So, we have recognized a need for some consistent time reference between the client and the server. And we recognized that in the last video when we saw that we needed to put a tick timestamp inside of the messages that we're sending across. Like when the client needed to send an input change request over to the server, I had to say, what tick do I want this change to occur on? So the only way that that can work is if the client and the server have some synchronized concept of what tick is what. For example, if the server started on tick 0 and proceeded as normal, then the client started up when the server was on tick 40. The client would be on tick 0. The server would be on tick 40. So the client might send a message saying, do this thing on tick 0. And it would get to the server, and the server would say, I've already processed tick 0. I have nothing to do. So it would drop that message. We don't want that. We need some consistent relationship between the client and the server so that it's convenient for us to send messages back and forth without having to do a bunch of math or guessing or anything weird when we receive a message to figure out what tick it's actually supposed to be applied on. So, the intuitive approach to how to sync these two things might be something like get the client and the server, and we're going to just use tick 20 as an example. Let's say the server started up, it got to tick 20, and then the client connected. The intuitive approach might be to just get the client and the server synced up such that they're processing the same tick at the same real-world time. So at one point in time, if you had the client on one PC and the server on another PC, and you had their monitors next to each other, and they were both printing out what tick they're doing, you'd be able to see that they're both processing tick 20 at the exact same time. So if we were going for that approach, we'd have to put a bunch of systems in to get them synced up and keep them synced up and make sure they're always processing the same tick at the same time. But let's just pretend that we're able to do that and that we end up getting that relationship. The client and the server are processing the same tick. So what would it look like in this intuitive approach for us to send an input change request like we have been in the past videos? Well, the client at tick 20 would say, I want to send an input change request. And this down here, let's say it's some tick in the future, like tick 24. So the client would be trying to send an input change request, and it would send it starting on tick 20. And we're going to say it arrives at the server on tick 24. So this is just a reality of networking. When you send a message, it's always going to take time for it to arrive on the other side. So in this example, we're saying it's taking 4 ticks to get from the client to the server. All right, so the server receives the message. And what does it do? So it receives the message. It sees that the message is for tick 20, right? Because that's the message that the client sent it on. And the client timestamps its messages with the tick that it's processing them for, which is tick 20. It's doing all its prediction based on tick 20. But the server is on tick 24, and it sees that the message is for tick 20. So, like I said before, all it can do is drop the message. So, this intuitive approach, putting both of them on the same time reference, is, in the first place, really hard to do. It's hard to get the client and the server synced up and to keep them on the exact same tick. But even if we were able to do it, we wouldn't gain that much because the approach that we're trying to take, where the client doesn't have to do anything weird and the server doesn't have to do anything weird in regards to how they're processing the ticks that are in messages, it's not helped by having this sort of relationship between the client and the server ticks. So the actual approach we're going to go for is, for the sake of I'm going to have to word this carefully because I'm not going to fully explain everything in this video. Some of it's going to come up in the next video, but for the sake of something like prediction, so things related to the client's own entity that the user is controlling, the client is going to be in the future. Now, I worded it so carefully because for other things like peer replication, that's actually going to be in the past, but don't worry about that yet. That's next video. For the sake of prediction and processing our own client entity, we're going to be in the future in relation to the server. So how that's going to manifest is the entire client tick, the tick that the client simulation is processing, is going to be in the future some amount in relation to the server's tick. So like say we're on tick 20 here, the client would want to be on tick 24 at this point. So when it sends this input change request, it timestamps it with tick 24. When it arrives on the server doesn't see that it's for tick 20 and drops it. It sees that it's for tick 24, and it just processes the message. Right? So we want to set the client far enough ahead in the future that messages will arrive in time to be processed by the server. So that's what client-server sync is all about. And this approach is, to me, the most straightforward. It's the one that makes most sense. There are other approaches, just something to keep in mind, especially if you're adding a feature called lag compensation. You might have an approach where you do want both of them to be synced up to the same tick, and then you do a bunch of complicated logic on the server side to figure out what should actually happen. But we're not doing that. There's security issues that go along with lag compensation, and the type of virtual world that we are making doesn't require it. We can handle a little bit of latency. So we're going to go forward with this approach where the client is ahead in time in relation to the server. All right. So what should we look at first? Well, let's go over this. So there's two things that are kind of obvious, but should be stated. When you are trying to keep the client ahead of the server, there's going to be two different parts of code that you have to maintain. One of them is starting the client ahead of the server. So when you're doing your connection process, you need to put the client ahead of the server before it starts processing its own simulation tick at all. And the second part of it is, while things are ongoing, you have to constantly keep the client ahead of the server. So you have to maintain this relationship. And we'll do that through something called an adjustment system. And that's going to be the complicated part of this video, going through how those adjustments work. But let's go through an example real fast to show the first part of this, just the simple part during connection. What does it look like to start the client ahead of the server? So let's get rid of this. And yeah, let's just get rid of all this. So let's say the server has been started. So it starts on tick 0, and at some point we get to tick 20. Now the client wants to connect. What does that process look like? Well, the client doesn't have a tick yet because it's not processing the simulation. It hasn't connected yet, but it's going to send a message. And the message it's going to send is, I want to connect. This can either happen through just setting up a TCP socket, or maybe you send a UDP message. However it happens, the client makes it clear to the server that it wants to initiate a connection. All right, so the server receives that. Now the server is going to respond with a connection response. So it's just going to send connection response. And what that connection response needs to contain, among other things, is the server's current simulation tick. All right, so the server is going to tell the client, this is my current tick. Now, let's put the lines here just to make it clear. If that happens here, And if yeah, let's do it like that. So if that happens at this point in time, let's say this is tick 24 again, it's not going to arrive at the client when the server is processing tick 24. So like I explained in the other case, the server is sending this message when the server is on tick 24. The message is going to contain the current tick, which is 24. But it's going to arrive at the client. Let's push it out farther so we have more room. It's going to arrive at the client when the server is actually at, let's say, tick 28. So in the client's point of view, the server is on tick 24 when actually it's on tick 28. All right. So the client is eventually going to need to do the thing that we actually want, which is get ahead of the server. Right now, when it receives this message, so this line's for tick 28, it's going to receive a connection response containing current tick equals tick 24. So that's what the message contains. It's saying, I'm the server and I'm currently on tick 24. What the client's going to do here is just make a best guess at some arbitrary number in the future to add on to this tick to try to get ahead of the server. So why are we doing some random arbitrary number? Well, we know that the server is farther ahead than tick 24. The client can make that assumption because we know that messages always take time to travel. We haven't yet established how latent our connection is. We don't know how many ticks worth of time it takes to send a message from the server to the client. But having that information wouldn't be very useful right now for us. We don't really care to maintain a bunch of code to do something like pinging back and forth to establish an average latency, because it just doesn't matter. At this point, all we want is to get somewhere in the ballpark, because we're going to have this whole big system that if the client doesn't reach the ideal number that it wants to be at, this system will take care of it. So we're just going to make a guess. In the amalgam engine, it's just the number 5. Like when we receive a message, we see what the server's tick was when it sent the message, and we just add 5 to it. And if that's enough, then cool, we're good. If not, the other system will take care of it later. So that's what this is going to do. Receive the connections response, contain the current tick. Set current tick to 24 plus 5 equals 29. And it's just going to start processing its simulation from there. So that's the entirety of how you start the client ahead of the server. You do your connection, do your handshake here, server responds with its current tick, and then you just add some number to it, and you try to get yourself ahead of the server. So that's the easy part. Now we have to get to the hard part, which is the adjustment system. What the adjustment system is going to be is either a unique message that the server sends every once in a while, or a couple of fields on the header that the server attaches to every message. And the adjustment system is basically going to say, if the client sends a message and it's received by the server late, actually let me reword that. If it's received by the server too late or too early, right? So if the server's on tick 24, anything earlier than tick 24 would be bad because the server can't process it. Tick 24 itself would be just in time, so that's maybe fine. Tick 25 and 26, those are kind of the sweet spot. That's enough room where if the network conditions change a little bit, we won't have to drop a message on the server side. So +1, +2, +3 is around where we want to keep messages. But if they're at +0 or negative, or if they're at +4 or more, so if on tick 24 we received a message for tick 28, we want to tell the client, hey, you can back up a little bit. you don't have to be sending stuff so far in the future. You can get closer to my own tick and it's fine. We have a good enough connection that you can do that. So that's the whole goal of the adjustment system, is the server being able to tell the client, based on what you have given me and based on when the message you've given me was received, you need to go forward or backwards in time. And by saying you need to go forward or backwards in time, we're saying you, the client, need to actually move your simulation forward or backwards. All right? That's a bit of a hard thing to get your head around. So I got this for you. And it's the very simple theoretical understanding of what the adjustment process entails. Right? So, like I said, we have forward and backward movement. So let's say the server's on tick 24 and we receive a message, or let's say the server's on tick 24. We ideally want to be receiving messages for a current tick plus 2, because like I said, that gives us good wiggle room. But we receive a message for tick 22. Yeah, let's say tick 22. So we receive a message that's 2 ticks behind us. If we have enough data at that point to determine that the client needs to move forward and that wasn't just a lag spike, then we can tell the client, hey, move forward by 2 ticks, or maybe even 4 ticks if we want to get closer to our plus 2 goal. So when we tell the client to move forward by, let's say, 2 ticks, we go through this process. So when the client's next tick comes around, it needs to process multiple iterations until it is at the current tick plus 2. And that's if we're trying to move forward by 2 ticks. So what that means is, in your client simulation processing code, you need to actually check, has the server given me an adjustment? And if so, I need to process a bunch of ticks at once until I catch up to where the adjustment has told me to be. So you're processing a bunch of ticks at once in order to go forward in time. All right? If we're doing the opposite, if we're on tick 24 and we receive a message for tick 28, maybe we want to tell the client to go backwards 2 ticks. Well, the client can't go backwards in time because it would have to reverse its simulation. And like we said in the input replay process, reversing is complicated and not really worth it. Instead, what we do is we just pause the simulation for however long we want to pause it. So to go backwards for 2 ticks, to take our current simulation tick on the client and make it 2 less than it currently is, we're going to spend 2 ticks doing nothing. So if you get a message from the server saying adjust -2, then the next 2 ticks that come around, you do nothing, meaning you don't even process or you don't even advance your simulation tick. So if the client is on tick 24 and the server says adjust -2, then it's going to process no farther than tick 24 for 2 ticks. All right. So that theoretically probably isn't that hard to get your mind around right now. It's a simple enough concept that when you're just looking at it at a high level, you can kind of see what's going on. The client's going forward and backwards, and the server's staying in one spot. And based on where the how much of a difference there is between the server's current tick and the messages that it's receiving from the client, it'll tell it to move around. So that's fine. Where this really gets brain bending is when you have to go apply it. Like the implications of this. When you have to move a simulation forward or backwards, and you're also doing prediction, and you're also doing NPC pure replication, like, it gets complicated. So expect that, understand that it's going to be tough, and you might have to go through multiple iterations on these systems. Just prepare for it to not be very straightforward. But without going too far into the practical implementations of this in this video, because we're going to do another video later where we actually do that, I do want to give you some amount of stuff to work off of if you're looking to do this thing. So one thing that I do have for you is I have a networking notes doc. So this is a Google Doc where I've written a bunch of notes about stuff that I've come across and stuff like protocols for the Amalgam engine, different features, how different things are implemented. And then I also have random stuff, like in here I have exploration of some different serialization libraries, some data that comes out of them. I have some load test results. But the important part is up at the top here. So without getting too far into the implementation, I can show you what does this look like in the Amalgam engine. And what it is I've decided instead of sending messages from the server to the client whenever an adjustment needs to happen, I'm just going to always have adjustment information in the header. And the reason for that is I always have to send these 2 bytes in the header anyway. And you can ignore what these are. It's just a count of how many messages are in the message batch. This is a batch of messages. And this thing is a value that's used for advanced delta encoding at a tick level. And you don't have to worry about that yet. We'll talk about that in advanced high player count network features. But I always have to send these 2 things. So I'm always going to be constructing and sending a whole packet for at least these 2 bytes. So throwing 2 more bytes onto it really costs nothing. So I get these 2 bytes for free, and the benefit is having these 2 bytes in the header, instead of having to construct and send a specific message when adjustment needs to happen, allows me to have pretty simple code to maintain what values need to go into this header, into these fields for each client. So I could have small code size on the server side and the client side for managing this level of the adjustment system. And the extra size that adds to the message pretty much is negligible. So that's a little peek into how an implementation of this might look. To get into the actual values, if you haven't read it already, this is the tick adjustment, the thing we were just explaining. So +2, -2, whatever. It's a signed byte. Then we have another thing called the adjustment iteration. Some people call this a generation instead of an iteration, but it's an unsigned byte, and it's what allows us on the client side to not double process an adjustment. So because we're sending this adjustment all the time, it's in the header on every message batch, and there's some lag between the server sending an adjustment and the client confirming that it received that adjustment and applied it. The server will end up sending multiple messages that have the same adjustment. So we end up having this adjustment iteration, which allows the client to say, have I processed this tick adjustment on this iteration yet? Or have I processed this generation of adjustment yet? If not, then I'll apply this adjustment to my tick. If I have already processed it, then I won't apply it because I've already done it. And eventually the server will go back to sending a 0 here once it receives the confirmation that we've applied our adjustment. So a little peek into how that works. Don't want to get too far into it because, like I said, we're going to eventually do a practical video where we touch it more thoroughly. But what I will do in the meantime is I'll put links to the relevant classes in the description here, so you have a little bit to work off of. Yeah, so I think that's most of it. The last thing that you need to know is just what to do when a message is dropped from the server's point of view. And what needs to happen there. We've already talked about it on the client side during prediction if we detect that a message was dropped. But on the server side, if a message is late and we have to drop it, then we have to end up updating the client somehow to let it know as fast as possible that a message was dropped and that it should stop predicting whatever state that it was predicting based on that message. How we actually do that kind of depends. You might be able to get away with just immediately sending an update to the client that you had to drop a message for. And based on that update, it can say, oh, I'm predicting incorrectly, and update itself and fix itself and everything. But if you have more complication than you're able to infer based on that immediate update, then you may have to send a specific message that says, hey, you are this client. We dropped your message for this tick. So handle it however you need to. But that's it. So that's client-server sync, including how adjustments work. Getting a little complicated. The last thing in this core set of basic networking concepts is peer replication. And it's probably the most complicated to explain. Maybe not. Maybe this is the most complicated. Maybe we're back on the other side of the hill. But either way, look forward to that. I will see you there.